Hey, good morning, chemistry team, coming at you again for the 150 somethingth time. There's going to be so many. We're going to get all the general chemistry videos here, all of them, lectures and labs. So we're focusing on our lab journey right now and something you may end up doing in lab. Hopefully, you won't have to. If your technique is good and you can do multiple runs on some kind of experiment and get really good precision, say you do 4 or 5 runs and they're all pretty tight, right? If you get a PPT rad, about 1 parts per 1,000. Hey, you can keep all those data points. But the problem is we do multiple runs, right? You should, because if you just do one run, how do you not know you screwed it up, right? You want to do a lot of runs and see if you've got some precision going on. That's the whole point. It gives you confidence that your technique is right. And another reason you want to do lots of runs is to minimize random error, right? So the more runs you do, the more it minimizes the effect of random error. And you'll see as you get lots of data points, if you do lots of data points, you got to do statistics on it. If you do a statistical distribution, we'll draw on the next board, you tend to almost always get this beautifully symmetric curve or a Gaussian curve that converges on the center. The most common, so if you do say 10 runs, you'll start to see numbers starting to repeat. It's like, oh, they're converging in on this one number with a few straying to the side. So you get this average in the center where most of them are around that value. We'll draw that on the next board and analyze this Gaussian curve. But it tends to do that, converging on the average or the mean, depending on how you think about it. But there's a downside to this. The more runs you do, the more likelihood you're going to screw up, possibly, right? You forget to condition something, a dry titrating, and you aren't looking at a drop, goes off, even if you have good technique, it's possible, your phone, well, you shouldn't have your phone ringing while you're in lab, right? Get rid of the phone, get rid of distractions. Maybe you pick your nose or something, lung contaminate. Oh, I'm just kidding. Well, I don't know, maybe you do. Something you understand could happen that's an unintended consequence. So very, very commonly, you might say you do 4 runs or something, you'll see 3 of them are pretty tight with a good precision, and one of them just looks a little weird. Like, which one of these doesn't look like the other type thing? We call that an outlier. The likelihood of an outlier increases dramatically the more runs you do, but you want to do as many runs as you can with the time limit to minimize random error and to show that you've got decent precision. So what do we do if we got this weird run, right? This causes an outlier. So I'll say this creates an outlier. It's just one that you're like, it just, something must have happened there. Now it's possible you screwed up. Oh, I spilled. Okay, well, we can eliminate that one because you spilled it. But if there's nothing obvious that happened, we can't just, say, oh, I don't like that data point and get rid of it. You have to prove statistically that that's a statistical outlier in order to eliminate it. That's the 4D rule in chemistry. You may hear the term, I think the Q test or something in statistics. I highly recommend you take it if you're going to go on in chemistry or any kind of science. I highly recommend you take a statistics test because in science you're going to take data sets, not just one data point, data sets, and you have to do a statistical analysis. Highly recommended. So let's look at this Gaussian curve and then how we can perform this 4D test and what it means. What's this 4D deal mean? And then we'll do an example. So it's not hard. It's just tedious because it's statistics, multiple steps. It's like, almost like calculating a PPT rad or something. It's very similar to a PPT rad calculation for calculating precision if you want to review that. Here we go. All right, while my neighbor has their lawn care done, I had to sit here and wait for the lawnmower to get as far away as possible. I'm like, oh my God, this is boring. Let's pet my cat here for a while. Let's take a look at the statistical distribution. I'm not here to teach you statistics. Take a statistics class on that. I'm just going to show you a snippet of what we as chemists need to use to get our job done. Like, let's get rid of that really ugly looking data point that doesn't seem to fit well with the other ones. Can we? Right? Doesn't mean we can't. Just because we perform the 4D test doesn't mean it's going to work. And if it doesn't work, we have to keep that data, that outlier. If the 4D rule doesn't work, that outlier is still statistically a decent data point, whether you like it or not. So sorry, lo siento mucho. But if the 4D rule does pass, then we can toss that data point as a statistical outlier like it never happened. Awesomeness! We love statistics. Yeah. So that outlier may be statistically eliminated using this 4D rule, which I'm going to talk about the statistics first, then we'll go through the steps of calculating our answers to the 4D rule and whether it works or not. So again, the more data points you do, the more they'll converge on an average. So let's call that the average or mean. And you'll get this tends to be a symmetric, I'm not a lot of bananas, a symmetric distribution. You see this happen in a lot of stuff outside of chemistry as well. This pattern seems to happen a lot, right? So you get this purple curve, you get this distribution of data. And the more data you get, the more likelihood you might get an error that happens way out here. But the majority of them are going to fall right in this range. And you can go research what's called a standard deviation, right? It's just a distance from the mean that encompasses a certain percentage of the data. So if we look at one standard deviation on either side of this mean, that'd be about 68% of the data points, right? That would encompass the majority, a good over, the broader half of them. If we went to two standard deviations on either side, right here, see the two standard deviations, that would encompass about 95% of the data points. If we went, it gives you kind of a 95% confidence level that your value falls in that range. If you go to three standard deviations on either side of the mean, 1, 2, 3, 1, 2, 3, boom, that would encompass 99.7% of the data. So 99.7% of the time you do a measurement, it's going to fall within three standard deviations of it. Another 0.3% might fall outside of that. And that's what we call the outlier. But if you want to have a really high confidence level, you can go to four standard deviations on either side. 1, 2, 3, 4, boop. 1, 2, 3, 4, boop. That would be a 99.993% confidence interval. If a data point fell outside of four standard deviations on either side, we call that the outlier region for us. We're 99.993% confident that's a bad data point, right? We can get rid of it. That's a really high. I mean, a lot of people are okay with the three standard deviations. We're going to go to 4 though. And if the 4D rule works, we have a supremely high, almost not 100%, but I mean, very close to 100% confidence that is a bad data point due to an error, and we can toss it statistically, feeling good and confident about our decision. So what we're going to do, so this 4 standard deviations are what we chemists call 4D, right? Not in all the statistics stuff per se. So we'll call that the 4D, and that's where it's called the 4D rule. Essentially what we're going to do, if you have a bunch of data points and you got one that looks weird, we're going to take all of the data points other than the outlier, the one we're trying to get rid of, and we're going to calculate the average of that. We're going to calculate the absolute deviations of all of those values from the mean, like a PPT-RAD calculation. And then we're going to calculate the average absolute deviation from the mean of all of the good runs, right? Everything except the outlier we're trying to get rid of. And then what we're going to do is we're going to multiply that by 4. 4 times the deviation, the absolute deviation from the mean. That encompasses all of this. If the outlier falls within this area, it's a valid data point. We have to keep it. If it falls outside that, we can get rid of it. Here comes the neighbors. So what we're going to do is we're going to take that outlier and do the deviation of that from the mean of the good runs and compare that to 4 times the average deviation of the good runs. And if the deviation of the outlier is bigger than 4 times the deviation of the good ones, but some of you are just hearing more snurky because as statistics speak. Let's go ahead and do it. But again, if the deviation of the outlier from mean of the good runs is larger than 4 times the average absolute deviation of the good runs, we can toss that data point as an outlier with an extremely high confidence interval. So let me pause this so the lawnmowers and weed whackers can go by. I'll write up the next board and we'll do an example problem. Here are your steps to calculating the 4D rule, almost identical to calculating the precision, the relative average deviation from the mean. Very, very similar. So what we're going to do is we're going to take all our data points and just list them from lowest to highest. Right? List them from lowest to highest. This step isn't really critical if it's very, very obvious what the outlier is. You're like, that's definitely whacked, right? But if you're not certain, go from lowest to highest, look at the extremes, the one on the far left, the lowest, the one on the far right, the highest, and determine which of those is furthest away from the others. That will be your outlier. More cat hair in the eyeball. This is a problem when you do all your videos with a shedding cat next to you. All right, determine the outlier, however you do it. Step 2, we're going to take all the data points except the outlier. Let's call those the good runs. We have no idea if they're good, but let's call those the good runs. So everything except the outlier, and let's just add them all up and divide by the number of runs and calculate the mean or average of those. All right. Then in the next step, let's calculate the absolute deviation of each run from the mean. So let's say we had 4 runs. 1 was determine the outlier. We'll take the remaining 3, calculate the mean of those, and get the deviation of each one of those, just like you're calculating a precision. And then we'll average them. So add them together, divide by the number of the good runs you're trying to keep. There's your average absolute deviation. Then what we'll do is multiply that by 4. So that's the 4D. That's where the name of the test comes from. 4 times the average absolute deviation of the good runs, omitting the outlier. That's our base of comparison, right? Think of that as that bell curve with that big spread with 4 standard deviations on either side, encompasses most of that curve. Then what we're going to do is now we can deal with, we haven't dealt with the outlier now, except till now. So we're going to take the outlier and subtract it from the mean in step 2, right? So we're going to get the deviation, the absolute deviation of the outlier from the mean of the good runs. Then we're going to compare that to 4D. So take the deviation of the outlier, compare it to 4 times the deviation of the good runs. If the deviation of the outlier from the mean of the good runs is larger, right? If it's larger than 4 times the average deviation, that means that data point falls on those far tails outside of that 99.993% confidence interval. Boom! You can toss it, right? It's gone. Like it never happened. Yay, hallelujah, thank you for statistics. But if the 4D, right, if we flip it, if the deviation of the outlier is less than 4D, that means it falls within that 4 standard deviation range, and we have to keep it. And you're like, oh, fortissimus maximus, I must keep it. There you go, that's how you do it. Let's do an example. Here's a very, very common example that you're going to be doing. It's actually an experiment I think I ran a long, long time ago. Of course, before my techniques were stellar. So we were doing acid. We had this unknown acid. We had to titrate it with a standardized base that we'd made. And we do 4 runs on it. All right. So we got 4 runs. Let's say run 1, 0.0955089 molar. It's good to 4 significant digits. Run 2, 0.0955625 molar. We're like, hey, feeling pretty good. Run 3. 0.0951115 molar to 4 sig days. We're like, And then run 4, right? Because we were a little hesitant on run 3. We're like, 1 and 2 were pretty close. Did a run 3. I'm like, wasn't happy with that. Let's do run 4, 0.0954515 molar. So still not as tight as those first 2, but a little bit better. So obviously run 3 is looking a little weird. So let's see if we can eliminate that. All right, let's just confirm that third run's our outlier. You can kind of see it. So let's list them all from lowest to highest. So run 3 was our lowest, then run 4, then run 1, then run 2, which was our highest. Obviously 4 and 1 can't be our outlier. It has to be one of the ones on the outside. So let's take a look at the difference between run 3 and run 4. 0.09511 to 0.09545, 1, 2, 3, 4. It's differing in the 4th decimal place, right? Now let's look at the difference between run 1 and run 2. 0.9550, 0.9556 differs in the 1, 2, 3, 4, 5, 5th decimal place, right? So these differ in the 4th decimal place. This differs in the 5th decimal place. So that tells me that run 3 is my outlier. So that's the one that I'm going to try to get rid of using the 4D rule. So let's look at those steps. If you want to pause the video and give it a shot, go ahead and go through the calculations. So go calculate the average of run 4, 1, and 2. Get the average deviation of each run and average that. Multiply that by 4. That'll be your 4D. And then take your outlier, run 3, do the deviation of that from the mean of the other good runs. right? Just subtract them and take the absolute value of that, and then compare them. If that's bigger than 4D, you can get rid of it. If it's less than 4D, you can't. And what's nice is we're effectively, the first couple steps are the same as calculating the relative average deviation from the mean for precision. So if the 4D rule actually works, you're almost done calculating the precision of your good runs. Yay! If it doesn't work, then you got to recalculate all the deviations, because then you got to include it. If it doesn't work, you have to include this, recalculate the mean, recalculate the average deviation. You're like, crud monkeys, right? But if it does work, it's a double score for us. So go ahead and see if you can do it on your own. I'll start doing step 2 on the next board here. How you doing so far? Statistics is a board filler, isn't it? Right, makes you bored too. Here we go. Let's start with run. So step 1, we identified our outlier. Step 2, let's calculate the mean of the 3 good runs. So we're not eliminating yet, but we're not including the outlier, which is run 3. So we're going to include runs 1, 2, and 4. That was the 3 closest that we had. Add them together, divide by 3. You're limited by fewest decimal places for averages, so they all have 5 decimal places. Our answer will have 5 decimal places, and I get 0.0955076 molar, good to 5 decimal places. All right, so that's, if we take the Gaussian curve, that's the very top in the center, right? Step 3, let's calculate the average deviation of all of those good runs. We're not worried about the outlier yet. So let's take the deviation of run 1, run 2, and run 4. We're ixnaying run 3 at this point, because that's the outlier we're trying to get rid of. So that would be the mean minus run 1, the mean minus run 2, the mean minus run 4. So I just wrote the mean 3 times there, and then I put in run 1 there, run 2 there, and run 4 there, and subtracted them, limited by 5 decimal places for each. So the deviation from run 1, I got 0.00000, 5 zeros after the decimal, with a vertical hash line 13 molar. Those are pretty close. For run 2, I got 0.0000549 molar, also good to 5 decimal places, not as close to the mean. And run 4, I got 0.0000561 molar, also good to 5 decimal places. And we want to average those. So let's take those 3 absolute deviations for run 1, run 2, and run 4. So I put the deviation from run 1 there, deviation from run 2 there, the deviation from run 4 there, added them together, divided by 3. That gives me my average, limited to 5 decimal places. I get 0.0000374 molar, good to 5 decimal places. Now that gives us one significant figure, but that just happens because we're limited to 5 decimal places. All right, that's the hardest part. Once you're done with that, the bulk of the calculations are done. So now let's move to step 4. We're going to take this average absolute deviation and multiply it by 4. That's our 4D. Go ahead and do that. I'm going to erase the board, calculate 4D, and then in step 5, we will calculate the deviation of the outlier. Finally, we bring that in step 5, calculate the deviation of the outlier from the mean of the good runs right there. Let's do it. We are past the hard part. Now it's all downhill after you calculate that average absolute deviation. So step 4, let's just calculate 4D. So we already know the average absolute deviation. We calculated that. That's the 0.000000374 molar, good to 5 decimals, and just multiply it by 4. Right? Doesn't matter how many runs you had. The biggest confusion students make, they think that number should be the number of runs that either you're keeping, the number of good runs, or the total number of runs. It has nothing to do with the number of runs that you perform. You could have done 50 runs, or 5 runs, or 4 runs, or 13 runs. It doesn't matter. That 4 stands for the 4 standard deviations on either side of the mean. So no matter how many runs you have done, you will always multiply the average absolute deviation by 4. So we're limited to one significant figure. So I get 0.0000149 molar, good to one significant figure. That is our standard for comparison. So if the deviation of the outlier from the mean of the good runs is bigger than that number, we can toss the outlier as a statistical anomaly. It falls on those far, far wings on either the left or the right-hand side of that Gaussian curve. if our deviation of our outlier from the mean is smaller than that, crud monkeys, we have to keep it because it falls within the 4 standard deviations. All right, Toe? So step 5, let's calculate the absolute deviation of the outlier. Finally, that's run 3, from the mean of the good runs. Okay, so let's take the mean of the good runs, 0.0955076 molar, we calculated earlier, and subtract the value from run 3, which is the one we're hopefully getting rid of. That was the 0.0951115 molar, good to 4 sig figs. We're subtracting, limited by decimals, 5 decimals, 5 decimals. We're good to 5. What? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Uh-oh, my number of decimals is off. What do you see? Notice I caught an error tracking my uncertainty. If I wasn't tracking my uncertainty, I would never have caught this. Tracking units and tracking uncertainty helps. Let's do the subtraction over again. 0.095. I think I'm missing a 0 here. Let's double check it. 0.0955076 minus 0.0951115. 1, 2, 3. Nope. 396. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I just have to, okay, so my calculation was correct. I just have to move my decimal point over. 3, 9, 6, 3, 9, 1, 2, 3, 4, 5. Oh, that's the wrong color. Ugh. There we go. 3, 9, 6, 1 molar. All right, so now calculate your the deviation of the outlier from the mean and see what you get. All right, we good to go for our final step. We've got, so for the deviation of the outlier from the mean, turns out the number was right. I just had the dashed line in the wrong spot. But notice I caught something there. So we go here, let's bring this down. Now step 6, let's compare them. So this is the deviation of the outlier, 0.000396 molar. Let's bring down the 4D up here from step 4, 0.000149 molar. Now obviously you can see the deviation of the outlier. That's out to the 4th decimal. It's 3 out to the 4th decimal, whereas the 4D is only 1 out to the 4th decimal. So it's a lot of zeros. So the deviation of the outlier is bigger than 4 times the standard deviation from mean. So this is a true statistical outlier. Falls outside on those far wings. That means that's a valid 4D rule. You have to prove that to get rid of it. And so we can eliminate that outlier. Right on? So what we can do if we want to calculate the relative average deviation from the mean, all we got to do is just go back to the deviation from the mean, right? And divide that by the mean times 1,000. That would give us a PPT rad. Yay! But if this didn't work, we'd have to go back and recalculate everything. That'd be a serious bummer. So make sure you're tracking units. Make sure you're tracking uncertainty to catch any potential errors. You saw that red flag go up. I'm like, oh, I thought there was an error. So it turns out it wasn't an error. I just had the dashed line in the wrong spot. Yeah, it happens to everybody, but we fixed it. All right, we can do the 4D rule. Hopefully, like I said, your data set's tight enough where you don't have an outlier. That's obvious, so you don't need to do the 4D rule. You just include all your data. But if you do, boop, this is how you get rid of it. All right, statistics.